Hey guys, had a request recently from long-term patron on the Patreon who had difficulties calculating the transformers, the power transformer and output transformer for the GT18 pay dirt amplifier, and he asked me if I could show him how to do it. So I thought it would be an interesting video to show you the process of um, calculating the transformer for using my spreadsheets. So in this case it will be a power transformer and a push-pull output transformer. So the amplifier uses two EL84 tubes, and it uses only a 6.3 volt tap, as you will see shortly. So let's start with the power transformer here. So I opened the Hammond transformer, which is I guess suggested for this amplifier by the builder. So of course this is like a universal transformer which has many different taps which are not used in this amplifier, and I talked to my patron about this, so we agreed that I will just use one tap for the primary, so to make it easy for him to wind it, and of course it will not be used. It's not a commercial amp, so we don't need all the different taps for the primary. On the secondary side, we will use only the B plus winding, and we'll only be using, and we will also be using the 6.3 volt winding. We will not use the 5 volts since we don't have a tube rectifier in this amplifier. Okay, and I will show a new spreadsheet that will be available soon on my website, so you can check that out later. So this new calculator for power transformers calculates also the amount of wire you need, and so it makes it easier to know how much material you would need for a transformer, and how roughly how much it would cost to build. So those are new interesting features, and of course you can follow along once it's available. So let's start calculating. I will open the spreadsheet. So of course the values here were used for some other project, some other transformer, and we will need to change it, so to change everything. So you will see me do it in real time. So first of all, when you want to calculate a power transformer, you would change the primary voltage to what you need. So my patron is in UK, so we would use 240 volts for the primary, and for the secondary we would divide it manually to two windings. So we have 275, but in the Hammond gives a really nice no load voltages, so this is what we actually need, and we see that it's very close to 600, so 297.6 volts per side of the winding. So let's say so we need 297.6, and that's at 144 milliamps. Okay. Okay, so let's go back to the spreadsheet, and we will use those. We will separate the windings as I said. So let's say 296.5, or got that wrong for sure. 297.6. Oh, of course, 297.6 at 140 milliamps. Okay. So 140 milliamps. And of course we have another winding which is 97.6, and we have 0.140. Okay, so that's our B plus winding. Then we go back to our sheet at 6.3 at 4 amps. 6.3 at 4 amps. Of course not 6.3, but 6.857, and we will split this one. It also has a center tap, so 3.429. Okay, 429, 3.429. 3.429 at 4 amps. 429 at 4 amps. 3.429 at 4 amps. Okay, I corrected the formatting, so now we can see all the voltages, and so we just double check 297.6 and 140 milliamps. We have 3.429 2 times 4 amps for the heater, and practically this is all that we need for this power transformer. Once we have all these things typed in, we are checking of course the frequency you should also set before going any further, so 50 hertz or 60 if you're in US, and then we have the magnetic flux density in Gauss, whatever. So this is the value that will work no matter what. So if you use 10,000, it will work for sure. If you have higher quality laminations like M6 or anything that's new and higher quality, especially if it's 0.35 millimeter thick, it's you can definitely go to 12,000 or even higher, up to 15. But to be on the safe side, we are going to use 10,000, which is a value that will work even with the higher quality ones, of course. So we have the minimum core cross section, which is calculated for us automatically, and this is the minimum that we need to have for this transformer, which is 11.8. And if you check the data sheet, so we can see that what they used, they have quite a lot more windings, so we can go for sure with the smaller one, but it's not really important. But we can just use this as a reference. So C is the dimension we are interested in. So this is the length of the laminations, and here we see that it's 3.81 inches. 3.81 times 2.54, we get 9.6 centimeters or 96. So it's EI 96 lamination type. Okay, so that means that we have to use we can try to go from that value, and if you want to check EI lamination standard sizes, here we have EI 96, which we see that it's 32 millimeters or 3.2 centimeters. The core, practically this center leg is, which is important for this measurement, is 3.2, so it's the column D here, and we would, so center leg is 3.2, and it's a good start to go with slightly higher, so not to have it like a square stack 3.2 times 3.2, we will go 3.2 times 4, which is the next standard bobbin value, and we see that we are on a good path, so this is practically good. Let's see, if we would have 3.2, we would be slightly under. It would still work, of course, but it's easier to just go with this to the next one, or the standard value, which is 4, and we see that it's green here, so that means that that we have a perfect selection here. The window length and window width, this is the always question from many people I get, that they're confused what this means. So this is in this calculator, you can see it here. So it's these two. So the higher value, of course, is length, and it's so 4.8 times 1.6. So we have 4.8, 1.6. Now this is not important for the number of turns. This is just important to see if we can fit wire, all the calculated wires with this configuration to the bobbin that we will be using. So so this is the important step. And here we have on the right already calculated number of turns for all the windings, and we have a recommended wire thickness. So this is the thickness which should be used. Of course, we cannot find always those calculated values, so we have to choose what we have. We shouldn't go under these values, so we should use either the exact value or calculated value, or we should go slightly larger. So the first one, we got 0.49. So we would go with the standard value of 0.5 millimeters thick wire. For the secondary B+, we got calculated 0.24 millimeters, and we would go with 0.25 millimeters, which is a standard wire gauge. And then we would go with the same here, 0.25, and for the other ones we got calculated values of 1.3 millimeters. Now here you can find these values, the thicker values, but they're very difficult to wind in home environment. So I would not suggest going with 1.3 or 1.4 thick wire. Instead, I would suggest winding two windings of the wire, which is half the thickness of the calculated value. So instead of winding 1.3 millimeter thick winding, we would wind two in parallel. So we would wind 2 times with the same starting point and ending point of the wire, and just in the end we would solder them together to the lead. So in this case it would be, if it's 1.3, of course we would go to the next one, which is 1.4, and divide it. So we would get 2 times 0.7. Of course, here we would use 1.4 still, just when it comes to winding, we would use it just for calculation's sake, so that we would know if we can fit it. Okay, and Okay, so we can see that we have practically so we have 101% of stack fill over here, which is not really a good thing because it means that we cannot fit the wire to the bobbin, and that's why the color is also not green, but it's some kind of reddish orangish color. That's why we need to do something to get it lower. Now, the way we can get it lower is by changing the quality of laminations. If we would change this to 12,000 with better quality, we would already be in the green. So it's enough just to use higher quality laminations, and you can see the number of turns significantly reduces. Also, for this amplifier, you could go easily with less current, because a pair of EL84s in push-pull and only a few, 2 or 3 ECC83s or 12AX7s all together are not going to draw more than 100 milliamps. So you could also reduce the wire gauge, use a lighter wire gauge. For example, use 0.2 should work just fine in this case. So you could also change the bobbin size if you had lower quality laminations and you wanted to be really sure that you have the right amount, right thickness of wire. You could go with, let's say, let's go back here to 10,000. So here you could go to the next standard size. Let's try that, 4.5 centimeters, and this would get you close. If you're experienced winder, you could wind it even when it's on the 90%, but it would be a stressful affair at home to do it. There is also 3.2 by 5, and that would also work, but the transformer would get a bit bulky and heavy. So if you have newer, higher quality laminations, or you are not sure what kind of laminations you have, but you can also experiment and try it with 12,000 GS, and this will cause only the laminations to get warmer, so it will just, the transformer will be running hotter, but in most cases it would still work even if you have lower quality laminations. If you have really just a really basic bad laminations, I would stick with 10,000 GS, because otherwise you might get a lot lower voltage than you would expect because of the voltage drop. So yeah, in our case, I would suggest going to 3.2 times 4 centimeters. If this is what you have, then I would reduce this this number here to 0.2, this number here to 0.2, and of course we would, if we reduce the current here to let's say even 120 milliamps, what we get, 23, okay. And as you can see, the wire thickness for the primary will automatically start decreasing if you decrease this value here. So let's say we go to 110, 110, and we get 0.45, which is a standard value for thickness, and we can reduce this one, which would to 0.45, and then we would get quite a good situation here. So so there are many ways to play with this calculator and to get optimum values. Of course, getting a lot lower than 80, 85 will be easy to wind and it will work just fine. But sometimes if you get a really low value here, you should consider using smaller bobbin or different laminations altogether, so one lamination lower. But if you're a beginner winder, I would suggest leaving a lot of room here, so getting as far away from 100% as you can to be able to wind and not worry if you're going to make it and to have room left when you put all the windings and insulation. So I would suggest using this method. Of course, with the current, you want to be careful. This takes a little bit of experience. Nothing bad will happen if you don't really. I mean, you could use 0.4 here as well. It would still work. It would just overheat a little bit. It would heat more, not overheat, but it would heat more. And you would get voltage drop. So let's say if you're expecting to get 297.6 and you don't use for this current rating, you don't use the appropriate wire thickness, you would not get to 297.6. When you measure it, you would get, let's say you would get 295, or you would get 290, or you would get 285. So your final B plus voltage might be too low, and that can be an inconvenient situation. If you go too far away, if you put too much, of course, if you use thicker wire, you will just get what you calculate. But you shouldn't really change this to a lot higher value, because if you get full voltage here, it can reflect in a quite high voltage for B plus, and it could be difficult to get that voltage down. So try to stick to the optimum. Don't go crazy with these ratings, because these ratings are optimum ratings. So using significantly higher values will not really lead to anything good. You would just get a really bulky transformer, which would not make sense. So it would be it's just a waste of space and material. But so just follow these. If you're a little bit more experienced with tube data sheets and the other schematics, amplifiers, you can check exactly in the data sheet how much current each of the tubes draw in this operation class or mode, and you can be sure that you are on the safe side for the current. So for example, if we have two EL84s and we know that each of them, let's say, uses 50 milliamps or 40 milliamps or 35 milliamps, we can calculate the correct value, and then we know that each 12AX7 uses only a few milliamps of current. So we can just be sure that we are in the ballpark and not going way beyond specs. So that's also another method which is a bit more advanced, but I will maybe go through it in another video. For this basic calculation, I think this clears it up. But if you have any other questions, you can post it in the comments, and I'll respond in the comments. So let's check. Let's see what we have here. So in this spreadsheet we have additional options. So it automatically calculates wire length, wire weight, the price. If you set the price per kilogram for these are from a couple of years ago, so not really relevant anymore, but you can use the exact value of the wire you're paying. So it will calculate how much of each of the wire gauge you need, and you can then calculate your total cost of wire. Also with the laminations, it will depending on what you use. If you use 0.5 millimeter thick laminations, it will just calculate how many you need. So let's say 80 pieces, which is going to be 1.88 kilograms in this case. This is only precise if you know the exact weight of your lamination, so you would have to put the values here of the ones you're using. So it's also a topic for another video, but at least you should know the number of pieces that you would need. So that's a better thing to consider, and that's pretty much it for calculating the power transformer. When it comes to the output transformer, we have also the data sheet from Hammond, and for this particular amplifier we would need 7.6K, so 7,600 ohms for primary impedance. This is the important value we need, and we have 4, 8, and 16 ohm taps, and the output power is 25 watts. Okay, so we open the correct spreadsheet, so we would hide this one. So we would use these values here. So that's, for the time being, we will just use one impedance, so let's say 16 ohms, and power is 25 watts. The effective load resistance plate to plate is 7,600. Minimum frequency, this is the thing that we will check, but we will discuss it a little bit later. But first of all, we want to see the magnetic flux density, which is a value that can be used for that also varies with the quality of your laminations. And if you have higher quality like M6 and similar laminations, you can easily go here to 10,000. Also for the minimum frequency, since this is a guitar amplifier output transformer, you can also go to like 60. It's not going to be, of course, exactly that value because it varies with different factors, but it's going to be close. The roll-off will be close to that frequency. It's usually going to be lower than that, especially if you have higher number of turns, as usually for these amplifiers you have. So you can choose. You can even go up to like 70. But I would stick to something between 50 and 60. So let's say if you have 60, it's plenty. So don't think of it as something that is going to like cut everything from 60 below. It's just going to have a smooth roll off of those frequencies. And okay, we have a flying plane. Good. So the next thing is we get 2,618 turns for primary. If you use the standard ones, of course, you can change this. You can see that all of these varies with depending on what you choose. So if you choose 70 here, you would get something similar. I find that having too low of number of turns, unless you have really high quality laminations, doesn't sound right. So having having a higher flux density or having a higher number of turns to a certain point produces a balanced sound between bass and high frequencies in a guitar amplifier. If having a lot less than that is going to sound thin, and if you have too much windings, like significantly more than 3000, it's going to sound darker. So yeah, I found out that usually somewhere between 2000 and 3000 is a sweet spot for most amplifiers using good laminations. So this would be a good number. And so for secondary we have 129. Since we're going to make it universal for 4, 8 and 16 ohm speakers, we will do that in just a second. So first we would find the DC plate current from the data sheet. Okay, we have class A. We have class B tubes, and we have class AB. So this is what we are interested in, and we can see that we have anode current of 2 times 46 at 300 volts. So as I said, we are close to the 50 milliamps. If the B plus would be like higher, this will go higher, but let's say it shouldn't be more than 60 milliamps per tube in under no circumstances. So we don't have to be really obsessed by those values, because the way this calculator works is it's very flexible and conservative with the values. So 0.046, 0.046, and the rest is calculated automatically. So we have it calculated for 0.21. Of course, we could in this case use 0.2 without any problems. Even 0.18 it would work, but I would suggest 0.2 in this case. And now we get to the window cross section, which is suggested here, and we can again cheat a little bit if we are not experienced, and we can check what Hammond used for their transformer, which again has additional windings. But let's see if they mention the dimensions here, or we need to open another one. Yeah, okay, they don't show us. Yeah, here 3. Okay, it's gonna be probably 75. 3 times 2.454, 7.6. Yeah, so it's EA76 Imperial, which is, we can use EI 75 metric. So as you can see, you can cheat in this way. If you are copying a known transformer, you can use the data sheet to be in the ballpark for this. And standard, you can check again in the power transformer sheet. You can check the standard dimensions for laminations, and we know this is the correct one for window length and width for this particular one. And we know that it's 25, so yeah, okay, so this is practically correct because it was also used for the similar amplifier. So we have 2.5 centimeters by 2.5 centimeters, which is 6.25, and that's this value here. It shows that it's not going to, that it's not optimum version, but optimum size, but you can ignore it because this value of 25 watts is exaggerated, and so it's all fine. So the important part is the stack fill. So if it's perfect, it shows 81.3%. So it means that we are right at the sweet spot for winding, and we have perfectly calculated transformer. But another thing is here we have also the wire thickness for the secondary, and it's 0.73. We can use 0.7 without any issues. Even 0.65, which is a standard value for 1 ampere. So yeah, I would go with 0.65 in this case. So that leaves us a little bit of room more. So it would be even lower than this, but we need to add, of course, the 8 and 4 ohm taps. But we would wind them all together. So it would not really take much more space, maybe a couple of % more only, because we calculated for 16, and the easy method to do it, of course, I should make a additional calculation in the sheet, but it's just too complicated because most people calculate only for a specific speaker they will be using. Fender also used to do that. So we're going to start with 4 ohms. We're going to start with 4 ohm tap, and we're going to check number of turns, which is going to be 64 with 1 millimeter thick wire, and then so we would need 64. We start with 64 at 1 millimeter. Then for 8 we have 91, which means 64 plus 27 and 0.8, and then we check for 16. We get 129 minus 64 minus 27 equals 38. So we get 38 turns at 0.7 or 65. I would go with 65. And so that would be our calculation for the transformer, for output transformer. Okay. If you have any questions, post them in the comment section, and I will be glad to answer. Hopefully this made some points clear here. Thank you for watching.